Good day, amazing scientists. It's your favorite sensei here again, Sensei Mohao, and it's good to be back again. I hope you all are doing good. I hope you all had a great weekend, and I hope you all are enjoying your school holidays. If you are new to our family, please press the subscribe button down there below and also that notification bell, so whenever we post new lessons, you'll be updated. On today's lesson, we will be doing notes. We'll be doing an introduction of physical sciences, one of the most hardest and challenging questions and topic, which is electric circuits. I know a lot of students are struggling with it, so I'll try by all means to explain it thoroughly and in an understandable way. So make sure you stay till the end of the lesson. Make sure you stay till the end of the lesson so that you can learn. I'll be explaining types of components, resistors in series, resistors in parallel, and I'll be also giving detailed explanations of definitions such as potential difference, the current, Ohm's law, and so forth. So I hope you enjoy the lesson. So now sit back and relax. So now in electric circuits we have this component. I know there are other ones, but like the rheostat is not here, but then for now I'll be focusing on only these ones because of the other normal ones that usually they are in tests, examinations, past paper, question papers. Usually find circuits that are made up of these components, including the buzzer and the speaker and so forth. So now electric components. So now when it comes to electric components, remember what are components. So now components are in essence parts of a circuit. There are electric parts of a circuit. So now basically circuits are built up of these parts. So these are just the building blocks of circuits. These are just the building blocks of circuit. You know, you can never have a circuit without wires. Why? Because of wires conduct electricity throughout the circuit. You can never have a circuit without batteries. Why? Because of batteries are the source of energy. So now these are the symbols that usually we use when drawing electric circuits. So now we have wire. It's this one. Let me find a different color. We have a wire. It's this one. So this is a wire. So you know, under we have different types of metals that we use for wires. We have copper wire, so forth. We have different types of metal wires. So basically we usually use copper because of copper, it's a good conductor of electricity. So secondly we have batteries. So remember we have battery and a cell. So what is a cell? What is a battery? A battery is it's two or more cells combined together. So a cell basically it's like this. We have positive terminal and negative terminal. This is a cell. But a battery is different types of cells added together, combined together. That is what we call a battery. That is the difference between a battery and a cell. For example, if now the cell is 1,5 volts, now a battery of 3 cells will be equals to 1,5 multiplied by 3, which is equals to 4,5 volts, which is the potential difference or the EMF of this particular battery, provided that it doesn't have any internal resistance. So I know maybe I may be confusing you with internal resistance, but I'll explain it in the next video. I'll make another video where I will be explaining internal resistance in and out. So now let's continue. We have a voltmeter. What is a voltmeter? A voltmeter is this device that usually we use to measure the voltage in a in let's say, for example, let me just draw a simple circuit, ne? So suppose this is a resistor. So now let's say probably we have a voltmeter. Okay, let's say we have a voltmeter here on the battery. So what the voltmeter here will do is that it will record the EMF, or it will record the voltage that the battery supplies throughout the external circuit. Okay? So same here, it will record the battery that will, sorry, it will record the voltage that will be passing through here in this 2 ohm resistor. Okay? So just remember that a voltmeter records the voltage, V for voltage, remember that, guys. So now we have a resistor. So a resistor, most usually, many of you all know what a resistor is. A resistor is basically an electrical component that okay, let me make this example. You still remember whenever we were at okay, you still remember in forces, right? We have something called frictional force. Remember what is frictional force? Frictional force is basically the force that opposes motion. Remember, whenever, let's say, the force applied go to the forward, to the west, né? Sorry, the east, sorry, to my right, and then the force of friction will oppose motion, so that the either the vehicle will stop, né? So this is the frictional force, will go in opposite direction. It's the same thing as a resistor. A resistor, it basically stops the motion, but remember, the motion here is basically the current that is transferred in the circuit. So now the resistor, it's basically like the frictional force. It resists the motion. Yeah. So we have a resistor. It decreases. Sorry. Okay. Let me not explain it now, or stick to explaining it in forces, because I know most of y'all have knowledge in forces and vector diagrams, so hence why I explained it with a much simpler and similar explanation as compared to another definition. So, but in actual fact, a resistor is an electrical component, like I said, that resists electricity. It resists electricity, so make sure it reduces the current flow. Basically, it reduces the current flow in a second. Let's say for example, let's say probably we have there's a resistor in a bit. I'm just going to do a short circuit just to show you. Let's say probably the battery is 3 volts. So now, if we have a resistor, so remember, without the resistor, current just flows, without being reduced. Current just flows, current flows. But now, whenever we have, let's say probably we have a bulb, let's say we have a bulb. Now, whenever we have a resistor, or let's say we have a bulb or a speaker, what will happen is that current will just flow and flow and flow and flow. Maximum current will flow, and also maximum voltage will flow. So that the bulb or the speaker will end up bursting. Why? Because of there's too much current flowing, and then it is now too much. So now a resistor will reduce the current, so that any component here in this circuit will not burst. So now also a bulb is also it's also a resistor in essence. So a bulb is also a resistor, so it will have the same effect. Although a bulb will convert this electrical energy to light energy, it will be like our light source, but it is also a resistor, because of it will also reduce the current that is flowing. Hence why it is also a resistor. Ne? So now we have types of switches. We have open switch, we have open switch, we have a closed switch. Ne? So now whenever we have an open switch, ne, what happens is that when the switches are open like this, ne, current is not flowing. The bulb, this one, will not light, will not glow. Ne? So now, because of current is not flowing, when current is not flowing, the current is just inside the battery. It is not moving out. Ne? So now, whenever current is flowing, you can see by virtue of this orange lines that, sorry, this shows the current flow from the positive, like it just goes, the switch is positive, the switch, the wire is the conductor of this electricity, and the bulb will glow because of what? The switches are opened. So let's go to another slide. We have a battery. Remember, like I said before, a battery is made up of 2 or more cells. So now, what is a battery? Ne? A battery, and what does it do? A battery converts stored energy, ne? Potential energy, we call it potential energy, into electrical energy. Ne? So now, it's that energy inside the cell or battery. Ne? This energy that is inside is converted to this potential energy, ne? And yet it's the stored energy. It will be converted to electrical energy. Why? Because of now this energy, what must happen? This energy, it's like it's chemicals here. Ne? So this chemical energy, we can say potential stored energy, it will be converted to electrical energy. Why? Because of these electrons will be the ones that will be moving, and then when the electrons are transferred, then current flows, it will now be electrical energy. Yeah? So now, the energy is so now this by virtue of a battery, yeah? By virtue of a power source, we know that energy can be converted in these 3 categories: either light, sound, or heat. We have a heater here. What energy conversion is it? Very good. From electrical energy to heat energy. This is a buzzer. Ne? A buzzer is more or less like a speaker. It makes sound. So it will convert electrical energy to sound energy. Good. And here, the normal one that we used to, light energy. So sorry for the noise in the background. It's just noisy here, but then I apologize for the noise in the background. So now I'm going to explain this phenomenon, ne, of conventional current, ne, because of it's more or less asked in questions, so like explain conventional current, ne. So now what you should know is that conventional current is the idea, like it's an idea of how current flows from the positive to the negative terminal in a second. Ne? So now remember, in actual fact, ne, this is okay. Let's check it. This diagram. Ne? This is the true one. This is the real one. That current flows from the negative. Why the negative terminal? Because of in this negative terminal of the battery we have electrons. So now there's electrons here are the ones that are agile and ready to move. So that they will move from this negative terminal, go all around the battery, then we'll meet again at the positive terminal. So, but the conventional current is the opposite of that. It's an idea, basically. Ne? So it is the opposite of that. It states that current flows from the positive to the negative terminal of the battery. So now let's continue. So now we are going to be doing definitions of this particular words that they use in physics, like potential energy, current. Ne? So
it's very crucial for you to understand what is the difference between current and potential energy, because of now they won't be using voltage, né? So even though voltage is the same thing as potential energy, but it differs because of there's a particular voltage that is inside the battery, there's a particular voltage that goes around the circuit, there's a particular voltage that is inside the battery, like the EMF, which is the electromotive force, which is the force or the maximum current that the battery supplies throughout the circuit. So now we are going to be doing potential energy. So what is potential energy? Between 2 points is the amount of energy transferred per unit charge between 2 points. For example, suppose we have this particular thing. Let me just take out a particular diagram here. I want a rectangle so that we can do let me change the color to black. Suppose this is our circuit. So now in a circuit, remember, in a circuit we have this point. We have a point. Let me just change the color to blue. We have a point, we have a battery, and then here or a cell. So between 2 points, the potential energy between 2 points is the amount of energy that will be transferred per unit charge between 2 points, which means from this point going, and then coming back to the other point. Let's say this is point A, this is point B. So now the potential energy is the amount of energy that will be transferred at a particular point in a charge. For example, let's say probably this is in current, and so in current we know and the voltage is gonna be the same So now suppose this is resistors in parallel. So now remember the point or the EMF, sorry, not the EMF, the potential difference between a particular point will be the potential difference or the voltage that will be moving from point A till point B. So this is the potential difference that we're talking about. Remember, potential difference and EMF are two different things. EMF is the maximum voltage or the maximum energy. We call it electromotive force. Is the maximum amount of energy that the battery supplies throughout the circuit. Supplied by the battery. So now this will be the formula that we'll be using. It's the work done over the charge. So because of the definition, the amount of charge transferred per unit, the amount of energy transferred per unit charge between 2 points. Henceforth, it's the work done divided by the charge, which is the formula. So now, negative electrons at the negative terminal of the battery have a high electrical potential energy. What does it mean? It means that the electrons will get energy from the battery so that they will be able to move around the circuit. So remember now, these electrons here are the ones that will move from this part to the other part like that. So now this the reason why we say they have potential energy, the ones at the positive terminal of the battery have a low potential energy, is because of, still remember the slide, that energy will move from the positive to the according to conventional current. So remember how this moves. It's like basically the electrons from this positive terminal are the ones that will move, and the ones that are here are stationary. It's more or less like that. Ne? Remember that it's something like that. Hence why I explained this first: conventional current and the electron current, the normal or true electron current, not the idea of conventional current. So now let's move to the current. So in physics, electrical current is defined as the net rate of the flow of charge. You can say basically is the flow of charge. So in a surface. So now, how do we calculate the current? So the current, we are going to use I. Remember the voltage we were using V. Current we're using I. So it's equals to the charge per unit time. So basically it's the amount. Remember, when it comes to the rate, we are going to be talking about the time also. So it's the amount of charges that flow through a point per specific time. It's the amount of charges that flow per specific time. So now it's easy for us to find this. Let's say probably they gave you all okay, we have 20 seconds, we have, let's say probably 100 coulombs of charge. So calculate the current. It will be easy because of you just saying 100 divided by 20, which will give you 5 amperes. So this is measured in amperes. Usually the symbol is A for amperes. For voltage was V, which is 4 volts. But here we're using A for amperes. So let's recap again. Electric current is the net rate of the flow of charges through a circuit. So now remember, now in series, let me just use this diagram here. I hope it is visible. In series, okay, let me just try to draw it. And here we have a bit. So now this is in series. So now we know that the current that will be flowing will be flowing, just like that. Flowing. So the same current that is supplied by the battery, the net flow of charge, is the same throughout the whole circuit. So now, but we know that in parallel, let me just do this. In parallel, current will divide here. Another part of the current will go throughout this route, and another one will go through this route, and then at this point they will connect again. So it's basically how the current flows throughout the circuit. So remember, the current that will be here will be like, it will differ. Why? Because of, if the resistor here is 5 and here it's 3, which means, sorry, the one or the resistor with the lowest resistance will allow more current to move, because of, remember that current is inversely proportional, or you can say indirectly proportional, because the higher the current, the lower the resistance. Current is indirectly proportional to the resistance. So that's it for today. I had a nice time doing this lesson with you, and I hope you all enjoyed the lesson too. Don't forget to like, to subscribe, and to share the video as much as you can to your friends, to your classmates. And for me, your favorite sensei, it's a wrap. Enjoy the rest of your day.